Hey, well, welcome back for more calculus. Today we're looking 8.2, section 8.2, which is accumulation and net change. So let's get right to it. We've got a Kyber crystal, simply known as Kyber or a lightsaber crystal. It's a living crystal and known in ancient times as Kyber crystal. Were rare, force-attuned crystals that grew in nature and were found on scattered planets across the galaxy. Important to us, in 2016's Rogue One, we learned that the Empire is mining Kyber crystals from the planetoid moon Jeddah. The ensuing conflict led to the first operational test of the Death Star's super laser, resulting in the destruction of the Holy City. So, calculus-wise, the integral is more versatile than just distance and displacement. We can use rates of any kind with an antiderivative to what we would say is we would accumulate whatever unit is in the rate. So we see that the rate here is units per unit time, right over here. And when we integrate that, what basically happens is we cancel one of the units of time, so that after the integral, we're just left with units. So pay attention to the units, the rates that are being provided for you, because they will give you a hint as to what you're going to be doing. In our example, we've got from t equals 0 to 10 months, the Empire mines Kyber crystals from Jeddah at a rate modeled by kt equals 2.2 plus 1.1 to the t power, 1,000 bushels per month. How many bushels of Kyber were mined from the beginning of the second month to the end of the third month of operations? Okay, over here, we see that K is provided with units of 1,000 bushels per month. Per month is a unit of time. So if I integrate here, I'm going to lose that per month. And the result will be in 1,000 bushels. So how many bushels of Kyber were mined? Well, if I integrate this again, we're going to get an answer in 1,000 bushels. That sounds like it would be the correct answer. So the time interval of interest should be a total of 2 months. So from t equals 2 to 4, and we're accumulating, again, 1,000 bushels per month. So when we integrate that, per month will go away, and we're just left with 1,000 bushels. So let's integrate this. Integral from 2 to 4 of 2.2 plus 1.1 to the t power. You might be asking or trying to remember, how do I integrate 1.1 to the t power? Here is your relevant antiderivative rule, the antiderivative of a to the x power. In our case, a is 1.1. That's equal to a to the x, natural log of a, plus constant. So when I integrate here, I'm going to get myself, let's see, the antiderivative of 2.2 is 2.2t plus, and then the antiderivative of 1.1, I'll go over here, and a is 1.1, a is 1.1, a is 1.1, and that looks like I would have 1.1 to the t power divided by the natural log of 1.1, evaluated from 2 to 4. Substitute the upper and lower bounds, and you still have something which you would need a calculator to evaluate. So that brings up that calculator rule. If you have a calculator, if you're allowed a calculator, don't bother trying to find the antiderivative. Just chuck the whole thing into your calculator, and that's going to be the answer. Of course, if you're not allowed a calculator, then you are going to have to go to an antiderivative like this. And this is how you would have to leave your response. And, without a calculator, that is good enough. So since we're just talking about, how the antiderivative and how integrals are used, we can use any of the methods we've met so far to evaluate those integrals. And just as a reminder, we have the rectangular methods, and the trapezoidal methods for estimating the value of integrals. This is what you would do if you do not get a function to integrate. So we're going to look at this problem over here. Kyber crystals must be transported from the surface of Jeddah to the interstellar ships hovering above the holy city in smaller transport vessels. On one trip, the rate RT at which Kyber crystals were loaded onto transport vessel N65 was recorded in the chart below in barrels per minute. How many barrels of Kyber crystals were loaded in that hour? R is given in a rate of barrels per minute. Integrating R will give me a response in units of barrels, which is matching what the question is asking. So it's good confirmation for me that I should be integrating R. There's no equation for R, so we're going to need to use a numerical method. 0, 5, 10, 15, 20. These are all spaced out by units of 5. So this is a nice place for us to use a trapezoidal method. The trapezoidal rule is to multiply delta x over 2 times the sum of the first f of a plus 2 times the next one plus 2 times the next one plus the very last one not multiplied by 2. And woo, look at all of those add-ins. That's a lot of things to add together. Substitute numbers. Here I multiplied everything by 2, but certainly not necessarily. You can just write 2 multiplied by whatever it is there. And you get 3,582.5. About 3,582.5 barrels were loaded onto the N65 in an hour. You probably might want to think about rounding this either to 3,582 or 3,583. As long as you have the numerical response here from the integral or from the trapezoidal method, you're okay to round it here in our answer because we are saying about as well. So you have to have both unrounded and rounded if you are interested in rounding it here. Of course, you can bypass all of that just by not rounding at all because it doesn't ask you to round anything. And there is a part B here. Use this answer to estimate the average load rate. Okay, so the average of anything in calculus is 1 over b minus a multiplied by the integral. We want to find the average rate. So instead of f, we're going to have a rate. So the average of rate is equal to the rate put into the average formula. We have a number for the integral, and it's 3,582.5. We get 59.70833. Dummy check. Does 59 look like a number that would fit with all the other rates? And yes, 59 does look like it's certainly within the values of what we're seeing here. So this looks like it could be a valid average rate. Kyber barrels were loaded onto N65 at an average rate of 59.70833 barrels per hour. Remember, if we're taking an average of rate, then the average rate will have the same units as rate. So if we're averaging R, then the answer is going to have the same units as R. Let's take a look at some important points here. So this is the idea of accumulation. So we're going to accumulate whatever the rate is measuring. You do have to make sure that the units of time matches. If you are given a rate in miles per hour and you're given time limits in minutes, well, those don't actually match. So you'll either have to turn your time units into all hours or all minutes. Integrals can be computed either analytically if you have no calculator, graphically if you don't have a function necessarily. That's of course if all the shapes were easy geometric shapes. And lastly, they can be approximated with numerical methods, which is what you would do if you have a table of values. Okay. The rate of consumption of oil during the 1980s in billions of barrels per year, I'm already mentally crossing off per year here to look at my units, is modeled with the function Ct equals 27.08 e to the t on 25, where t is a number of years after January 1st, 1980. Find the total consumption of U.S. oil from January 1, 1980 to January 1, 1990. So let's make sure the years match up. Actually, before we do that, let's figure out what we're doing. Sorry, getting ahead of myself. So we're going to find the total oil consumption. So that's the total number of barrels. So we're going to integrate the barrels per year, the rate of consumption. So if we integrate the rate of consumption, then we'll get the total number of things being consumed. Now we can talk about the units of time. This is in barrels per year. We're given things in years. So how many years is it from January 1st, 1980 to January 1st, 1990? Count this: 1980, 81. That's 1 year, to 82 is 2, 83 is 3, 84 is 4. So it looks like we're going to get 10 years. So it looks like we should be going from 0 to 10. So we're integrating from 0 to 10, 27.08 e to the t over 25. We're going to use a u substitution because u is t over 25, du is 1 over 25 dt, or dt is equal to 1 over 25 du. So we're going to do our substitutions. T over 25 is going to turn into u, and dt is going to turn into 25 du. I'm going to take this opportunity to also convert the units of the upper and lower bound into terms of u. So if t is equal to 0, then u is going to be equal to 0 over 25, which is 0. And if t is 10, u is going to be 10 over 25, which is 10 over 25. I'm not even going to bother reducing that. Okay, this is actually a very easy integral now. We've got 27.08 multiplied by that 25. I can definitely do that later. E to the u from 0 to 10 over 25. And let's substitute everything in, and you get 677 multiplied by e to the 2/5 minus e to the 0 power. E to the 0 power is just 1. So we can just turn this into a 1. And either leave it like that. Well, no, I would say leave it like that. There's no reason for you to grab your calculator because that is a perfectly reasonable answer in terms of calculus. If you were going to grab your calculator, then there was no point in finding the antiderivative, unless you're showing off or unless you have to find the antiderivative. But in a question that was a calculator question, you're not expected to show antiderivatives. So let's get this response evaluated. 322.965. 322.965 billions of barrels of oil were consumed between January 1st, 1980 and January 1st, 1990. You might ask, where did those units come from? And they come right from the question here. Billions of barrels per year was the rate for C. Cancel out per year, and we get billions of barrels, which should be the units after we integrate. So that's it for this one. Hopefully that was pretty easy for you. A lot of review things here. The only new thing here was really conceptual, and even then, I don't know if I would consider it new. So we'll see you next time. Have a good day.